Okay, hello everyone. Welcome to today's lecture. Last time we were talking about, had we started discussion about interrupts? I guess yes, right? So we focused at basically on what is the difference between polling and interrupt based mechanism of handling events. And then, I don't remember, let me quickly check what we covered in the previous lecture, right? Yeah, so we covered the difference between polling and interrupts. What is advantage, disadvantage of both sides. Then, uh, like, we found that we need to enable the interrupts at global level. There two-level mechanism. First, you need to set the I flag in the SREG register, and then the individual interrupts. Then we went through the steps in executing an interrupt. We talked about what is interrupt service routine, and we also covered the discussion about interrupt vector table. And then we started talking about interrupts, timer interrupts at Mega 328P, but we were not able to complete that. So we'll continue from that point today. So we have covered how timers work in ATmega 328P. There are three timers, timer 0, 1, and 2. And all three of those timers they can be used both in the polling mode and in the interrupt mode, right? So when we say polling mode, it basically means, as we have seen in previous example, that we continuously in our code continuously monitors a flag of an interest, like for example, the overflow flag or output compare flag. And when it is set, then we take an action. Now we can do exactly the same thing using interrupts. So for example, when the overflow happen, instead of monitoring the flag, overflow flag, we can tell our microcontroller, it's your job to monitor that. Okay, the overflow flag is set, and when that happens, go and execute the interrupt service routine, which is interrupt service routine, which is related to or which corresponds to handling that event, right? So for that purpose, if we want to do the interrupt-based handling of event, for example, the overflow flag. So for that, we first need to configure or set the bits in three registers, depending upon which timer we are working on. So there are three registers, timer interrupt mask registers, one for each counter. So TIMSK 0, 1, and 2. So TIMSK 0, for example, if you let me select the pointer. So if you look at this register TMSK0, it has three bits. All other bits are not used. The least three significant bits are used. So this bit at index 0, timer overflow interrupt enable 0. If you want to actually raise an interrupt when the value of the timer overflows, and you want to raise an interrupt, then you have to first write one in this bit position to enable the interrupt. Similarly, if you want your microcontroller to raise an interrupt when the value of the timer counter register matches with the output compare register A, so for that you have to write one in this second bit position. And if you want your microcontroller to raise an interrupt when the value of the timer counter register matches with the value of the output compare register B, then you need to write one at this bit position. By default, all these bit values are zero. So when you reset your microcontroller, so all the interrupts are disabled. So you have to explicitly enable them. Even the I flag in the status register is also by default set to 0. So you have to enable it explicitly. Okay, so same goes for the three bits of the TIMSK2 register, and then for TMSK1 register, which is for timer 1. So the least three significant bits, they have the similar meaning, the only difference that they apply to the overflow interrupt, output compare interrupt A, and output compare interrupt B of the timer 1. And then the bit at position 5, it is for input capture interrupt enabled bit, which we haven't covered, so we are skipping it at this point. Okay, now last time we were actually at this point, we were trying to understand this, we were trying to write a assembly program where we wanted to enable the interrupt and wanted to write the ISR. So, but we stopped because the example code we had, it was written not for ATmega 328P, but it was written for ATmega 328. So, which mean that the registers used were different as compared to ATmega 328P, and then it can become confusing. Now I have fixed the example, and we can go through it now. So, what we want to do in this example is that we want to use timer 0 to generate a scale wave of period 8 microsecond on pin port B.5 at 8 megahertz. So our clock is running at 8 megahertz, and we want to generate a scale wave of period 8 microseconds. So which means that signal stays high for 4 microseconds and then stays low for 4 microseconds, right? Clock frequency is at 8 megahertz. So and also we don't want to do only that thing. What we want to do is that we also want to transfer the data from port C to port D. So we have 8 LEDs connected at the output port D, and we have 8 switches connected at the port C, right? So we want to continuously read the switch values and display them on LEDs, but in the meantime, we also want to generate a scale wave, right? Now it's mean that we are doing two different things. Uh, are we are doing two different things in not simultaneously, but in a way that it appears like simultaneously. However, this illusion of simultaneous doing simultaneously multiple tasks, have a look how we can do this. So uh, first, what we are doing here is that uh, so first, what we are doing here is that we are putting the directive .org 0x0, and then we are putting the jump state, writing the jump statement jump main. So basically, what we are telling our assembler is that at address 0 of the uh, code memory, put the jump instruction jump main. Why? Because uh, if you remember the interrupt vector table from last lecture, so when you reset your you reset your microcontroller, so that is an interrupt, right? So when you press the reset button, and when you press the reset button, the ISR of reset interrupt is executed. Interrupt service routine of reset interrupt is executed, which is located at address 0. So that's why at address 0 we are saying we are putting simply a jump instruction to the main. So we actually want our microcontroller to start execution at main whenever the reset button is pressed, right? Now, the next thing we are doing is that uh, at address 0x0020, we are putting a jump statement to a label named as Timer0 Overflow ISR. So basically, again, how I know this address 0x0020, because if I go to interrupt vector table, let me show you. So yeah, here if you go to interrupt vector table, you can see that uh, the address for reset interrupt is all zeros, and the address for uh, timer counter 0 overflow is 0x0020. That's why in our program we are putting the jump statement in at that address, so that when the interrupt happens and the microcontroller goes to this position for starting the execution of the ISR, so then it will jump to the to our label, which we will have on next slide, which corresponds to our body of the interrupt service routine for timer 0 overflow, right? Other than that, what we are doing is like, okay, now we want to store our main program at address 0x100, because we don't want to put it at the addresses at the start of at the start of the address range, because the locations at the start of the address range, they are reserved for different types of ISRs. So that's why we want to move down in the address space, and then we are putting our address, our main program at location 0x100. And then after that, we are saying, okay, now initialize the stack pointer. I'm not going through this code because we have seen it multiple times in previous slides. Uh, and then we are configuring the port direction. So we are setting the pin B5 as output, right? And we are setting the port C as input, right? And we are setting port D as output. So after the pin configuration, we are done with that. Now what we need to do is that we need to enable the timer interrupt, and also we need to put the value uh, in the timer registers, right? So let me first let me first walk you through this timer initialization code. So here what we are doing is that we are putting -32 in R20 and writing that to TC and T0. Why -32? Because that is the value which you need to generate a delay of 4 microsecond, right? We remember we said that we want to create a scale wave of with a period of 8 microsecond, which means that after every 4 microsecond we need to toggle the output, right? So if you have 8 megahertz clock, so you can do the math. So 1 hour 8 will be your 1 hour 8 will be your period of the clock, and then you can divide 4 by whatever you get, like 1 hour 8 megahertz. So what you will find is that you will get the value of -32. So that's why you are loading the value of -32 in R20. And we have actually seen in previous slides that how you can find the number which you need to put in a register to generate a delay of a given amount, given time period, right? So you are putting -32 in R20 and then writing it into the timer control register. The other thing you are doing is, remember, we want to use our timer in the normal mode and operating at the original clock, the same clock which is on which our microcontroller is running, and we know that it is running at 8 megahertz. So what we are doing is that we are writing 0 to the timer timer counter control register A of timer 0, right? So I don't want to go back to the slides from the timer the topic where we're discussing the timer. But if you write 0 into the timer control register A, so basically you are selecting the mode, and here you are putting 1 in the timer control register B of timer 0, which will actually use the same clock as the AVR microcontroller, and it will start the timer. But before setting the timer, what we are doing is that we have enabled the interrupts here. Okay, so how we need to enable the interrupt? So for that, we need to write the value in TIMSK0 register. What is TIMSK0 register? We can go back here, right? So we simply want to put 1 here in this bit. Okay, so that's why. So here we are saying, okay, shift 1 to the left 0 time. So which means don't shift it left. So you will have a binary code of like 7 zeros and then 1 in the least significant bit position, and then you are writing that value in TIMSK0, which means that you are enabling the timer overflow interrupt for timer 0, right? And but remember, whenever you are enabling the interrupts, you also need to enable the write 1 into the I flag of the SREG register, status register, right? So this is you can do that by executing the set interrupt enable instruction, right? So this will set I flag equal to 0 in equal to 1 in your status register. Now your interrupts are enabled, and after that, so now we are done with timer initialization. We have enabled the interrupts, and then we are saying, okay, now we are executing an infinite loop, right? So here you can do something else, like this loop actually represents that you are doing something else and you are not monitoring your overflow flag continuously, right? So for example, what you are doing is like you are simply reading the data from the port C, putting it in R20 and then sending it to the port D. So continuously you are reading the value of these switches and displaying them on the output. So you are doing some work, you are doing some task, right? You are not worried about your overflow flag as we were worried when we were using the polling, right? However, whenever the value of, remember we have placed the value of -32 in our TC and T0 register, right? So whenever it will reach to the maximum value FF, and then it will move from FF to 00, at that time point the overflow register will be overflow flag will be set equal to 1. It's mean at that time point your interrupt will happen, right? But you don't need to worry. Now as soon as the interrupt will be raised, at that time point what happened, let's say that your microcontroller was executing this instruction, right? And at that time point the interrupt occurred, so which basically means that your overflow happened, right? So your microcontroller will complete the execution of this instruction, but after that it will not go to the next instruction jump here. The control of the execution control of the microcontroller, or the next instruction that the microcontroller will execute, will be this one. Where let me go. It will be, the microcontroller will jump at this location, right? 0x0020, and at this address whatever instruction is stored, that will be executed. So the instruction that is stored is jump to timer 0 overflow ISR. So this instruction will be executed, and then microcontroller will go to this location here, because this is the first instruction at the provided label, right? So then this whole program will be executed. What is that, what we are doing in that program? Okay, before I go into like what we are doing in this ISR, so let me just explain it first at higher level. So this, all of this program will be executed, and then finally the return from interrupt instruction will be executed, which means, so before, whenever the interrupt happens, so we are assuming that interrupt happened at this point, right? So next instruction to be executed will be was PC is equal to jump. PC was equal to this one, right? Sorry, let me erase it and try to draw it again, write it again. So our PC was, so the next instruction that was to be executed was this one, jump here, right? So PC was pointing to this place when the interrupt happened. So when the interrupt arised, the what microcontroller will do is that it will put the value of the PC on the stack, right? I'm just indicating it by X because I don't know the address. Or let's say this is our address 29, right? So the microcontroller will put 29 in the on the stack, and then it will go to the address 0x0200, and at that address it finds this instruction jump to this label, so it will execute this instruction. So the next instruction that will be executed will be from this label. So then this whole program will be executed, and at the end when you say return if from interrupt, so what will happen, that 29 will be like so two things happen. One, uh, that 29 will be put back in the PC, right? And which mean that after this the next instruction that will be executed will be this instruction X, jump here, right? And the second thing which is happening as a part of as a part of execution of return and return interrupt is that I is set equal to 1, right? Why I is set equal to 1? Because when your interrupt happened, so microcontroller will by default set I equal to 0. It will disable the uh, global interrupts. Why? Because now it is going to serve the current interrupt, which is the timer overflow interrupt. So while it is serving this interrupt, it doesn't want other interrupts to happen. So that's why it is disabling the interrupts. But once it is done with serving the current interrupt, and at the end when we execute return interrupt. So as a part of execution of this instruction, I will be again set back to 1. Okay. Now, now let's have a look at what happens in the body of the ISR. So first thing is that, remember when we were using the polling, what we were doing, whenever our time overflow flag, we detect that overflow flag is set equal to 1, we have to clear it by writing 1 to it. But when you are using interrupt based handling of the events, you don't need to clear the overflow flag manually, because it will be cleared automatically on an interrupt. When the microcontroller will detect that an interrupt has raised, an interrupt has arrived, so the hardware automatically will clear the flag, overflow flag of timer 0, right? So you don't need to clear it by writing one in your code. Then what we are doing is like we are we are putting 0 in R20 and sending it to the timer control register B. Why? Because we are stopping the timer. Remember, our timer was running when interrupt happened, right? So yes, interrupt happened, but timer continues to run. So we want to stop it, right? So we are stopping it, and then what we are doing, we are going to like toggle the output at the port B. So we first read the current value from the port B register into R16, and then we load 0x20 into R17. So then we are doing the exclusive R. Why 0x20? Because we are toggling the output at pin 5 of port B. So 0x, when you convert into the binary, so you will get this one. So bit at position 1, bit at position 5 is 1. All other bits are zeros. So what you are doing is that you are reading first the current value of the port B into R16, putting 0x20 in R17. When you do the exclusive R, the bit at position 5 will be flipped, right? It will be toggled, and then you are writing R17 back onto the port B. So now if like previously the output was high, now it will be set to low, right? And then again you are loading the register, because again you want to generate a delay of 4 microseconds. So you again loading -32 in R20 and sending it to TCNT 0, right? And then again you are starting the timer by writing 1 in the timer control register B, right? And once you are done, so this is like all of this is body of your ISR, and then at the end you are executing return interrupt instruction, which will be like, again it will bring you the same point where this loop was interrupted, right, at the same point. So this is how you can handle the events, or for example you can handle the overflow or output compare match event by using interrupts instead of using polling. Any questions? No? Okay, we have another example here where we want to where we want to actually write a program to serve the output compare match interrupt of timer 0. So what we want to do is to use the timer 0 in CTC mode to generate a scale wave again on port B5, while at the same time data is being transferred from port C to port D. Actually, your this example is almost same as the previous example, with the only difference is that in this example we were using the normal mode, but here we want to use timer 0 in the CTC mode. But like just like for example last time, what we were doing is that when the overflow happened, we want the interrupt to be raised, and then we write an ISR for that. Here again we want an interrupt to be raised when the value of the timer counter register matches the output compare register, and then we will write an ISR to service that interrupt. Okay. Otherwise, everything is same. So let me walk you through the example here. Uh, the purpose of this is the first section is same. Like we are saying, okay, on the reset, jump to the main and start executing program from the main, right? And then here we are putting now this address 0x001C. Again, when you go to the vector interrupt vector table and look for the address for timer 0 compare interrupt compare match interrupt A, then you will find the address 0x001C. Actually, I can show you if you want. So yeah, this one here, if you can see 0x001C for timer counter 0 compare match interrupt. Okay, so you can always go to that table to find the addresses, required addresses for the to when you are writing ISR for a given interrupt. So the next thing we are doing is like we are at the address 0x100, we are putting the code of the main function. So initially we are setting the initializing the stack pointer register, and then after that we are configuring the port directions. So these are similar as in the previous example. We are making the port C as input, we are making the port D as output port, and we are setting the pin 5 of the port B as input, as an output pin. Okay, now, the next thing we need to do is that we need to initialize the timer, but this time we are using the timer in the output compare, we are in the CTC mode, right? So we need to know that what value we need to put in the in the output compare register of the of the timer. Now, you know, like if you are given the duration, like how long, what is the amount of the delay that you want to create, then you know how to find the value which you want to put in the register. So I'm not going like to explain, but let's say the value you come up after the calculation is 39. So what you're doing is that you are putting 39 in R20 and then sending it to the output compare register A, right? Then you are initializing the TCNT 0 register with the value of 0. So what will happen is that it will count from 0 up to 39, and then when the value will match at 39 in the next cycle, the output compare flag will be set equal to 1 and the value of the timer will be set back to 0, right? And then we need to write values in the control register A and B. So we are writing the value of 0x20. Why? Because this is the appropriate value you need to write to set the CTC mode. I don't want to go back into the timer slides to explain the register, but after the lecture you can actually go back and you can confirm or verify for yourself that by looking at the bits of the control register A and B, that this is the value you need to put in the control register A for setting the CTC mode. And then we are setting value of 1, or we are putting the value of 1 in the control register B, so which will actually use the internal clock without dividing it with any denominator, and then it will also start the timer, right? So after starting the timer, we are enabling the interrupt. Uh, yeah, so to enable the interrupt, we need to put the right value in the TIMSK0 register. So what is that value which we need to put? For that, you go back to the uh, this slide, and here we want to actually enable the output compare interrupt for output compare register A. So we need to write 1 here. We want to write 1 here, right? So that's why what we are saying, okay, like shift one time to the left, so which means you will get the binary value of 0 1 0 and then all 5 zeros here more. So you are putting that value in R20 and sending it to TMSK0, which will actually enable the output interrupt for compare register A. But that is not enough. You also need to set the I flag in the status register to enable the interrupts. Why are we setting the bit in port B to make port B 5 and output shouldn't it be DDRB? Are you talking about this instruction? SBI port B. Okay. So you are saying that to set the it as the output port, we should be writing in the port B register, right? Anyone who want to answer this question? Student is asking, why are we setting, why are we using this instruction SBI port B comma 5? This instruction here again, I'm like pointing to it, to set the port B as an as output port. Why are we not writing the port B register? Anyone who want to answer? Okay. So actually the thing is, this is instruction set IO bit instruction. So you have this port B register, right? And it has 8 bits, right? So this instruction is basically saying is that set the bit at index 5 of port B register. So let's say this is your port B register and this is index 5. So here you are saying write 1. So it will configure only the pin 5 of the port B as output pin. And we are interested only in configuring that one. Only one single pin, not the whole, all other pins of the same port. So the remaining other like 7 pins of the same port, they will not be affected. Okay. Yes, you are right. You can also write if you want. You can write, okay, uh, write in port B register, sorry, DDR-B register, the value of all ones. But then it will configure all other pins as well. Okay. You can also write, uh, let me go to the, let me go to the OneNote to explain it. It's trivial, and I was expecting that some of your friends they will respond to my question, but none did. So, okay. Week 13, day 1, right? So, here is your port B, pin 5, and we want to set it as output, right? Now, you are saying, why are we not using, oh, sorry, why are we not using DDR-B register, right? We can, if we write we write value of 0x20, which is equal to 0000, and then 0100. So what it will do is that it will configure pin 5 as output and all other pins as input, uh, right? But we don't want to, like, what we want to do is that we don't want to affect other pins. We want to keep them as they are. We don't know what is their status, right? So what we can do is that if we write this instruction set IO bit, uh, oh, I got your question now. Okay. I was like trying to mold your question, but anyway, let me finish and I will come back to your question. Okay. So when you say DDRB5, so now you are doing this. All other bits, they will retain their older value. This bit will be set equal to 1 and it will be output. Now, okay. I think the problem with the question is like with the code is like here it should not be port B, here it should be DDRB, right? Yeah, you are right. There is a mistake in the code. I just realized now. It should be set SBI DDRB, uh not port B. Thank you. Let me fix it. Yeah, and I was not paying attention to your question. I was like trying to make my own question and trying to answer my own question. Thank you. Yeah, thank you for for asking. Yeah. Okay. So where were we? Yeah. So we were talking about, I guess we were here at this point, that were enabling the interrupt by writing 1 at the bit position 1 of TIMSK0 register, right? And then we also need to enable the I flag in the status register SREG, right? And after that, what we are doing is that we in an infinite loop, we are simply reading the data from port C and sending it continuously to port D. So, but again, assume the same, let's say the same scenario that PC was the microcontroller was executing this instruction, and then the interrupt happened. And here we, when we say interrupt happened, it's mean the value of the TC and T0 register matched the value of 39, right? So then the interrupt will be raised. So when the interrupt will be when the interrupt arrives, so microcontroller will go and read the instruction from the location 0x001C and execute it. And that instruction is jumped to this label. So then it will jump to microcontroller will jump to this label and execute the instruction there. Now, before I go to like explain and execute these instructions, let me read these comments. So first thing is that we don't need to clear the output compare flag A of timer 0. Why? Because when the ISR, when the microcontroller jumps to like ISR, it will automatically clear the output compare flag A of timer 0. Okay, so we don't need to clear it explicitly. Okay. Also, we don't need to we don't need to set TCNT to 0. Again, there is a mistake. Yeah, so we don't need to set TCNT back to 0. Why? Because if you remember in CTC mode, how the microcontroller works, it starts from 0, then it continues incrementing its value on every clock until it reaches the value which matches the output compare register, which in this example is output compare register A of timer 0, right? And after that, the value of the TCNT 0 is automatically set back to 0. So we don't need to set it back to 0 manually, right? So after having said that, now what we need to do is that simply we need to toggle the output. So we are reading the port B, putting it in R16, loading 0x20 in R17, doing the exclusive OR between two things, and writing back the value into the port B. And then we are saying, okay, return back to the interrupt. So when now we return back from the interrupt, our TCNT will be equal to 0, right? And our output compare register, we don't need to like change its value because we have already written its value once, which is 39 already there. So we don't need to do anything extra, right? And the flag output compare flag is already automatically set to 0, right? So now what will happen is that you will have your data from port C will is sent to the port D continuously, but at the same time, if there is an interrupt, a scare wave is also generated uh, on the output port C, port B.5. Okay. Any questions? Okay, so if no questions, then let's move to our next subtopic, which is about external interrupts. So we have covered interrupts related to the timers. So we have not seen example for writing the, let's say if you want to write an assembly code to handle the interrupts related to timer one, we haven't seen an example for that, but it will be also very similar, just like example we have seen here. The only thing will be that you need to initialize the registers of timer 1 instead of, let's say, timer 0. And similarly, the addresses that you will use to store the ISR, they will be also different. And you can check those addresses from the interrupt vector table. Okay, so external interrupts, why we are naming them as external interrupts? Because the interrupts which, for example, which we have seen in the previous subsection are timer related interrupts, they were generated by an by a component which is like internal part of your ATmega 328P microcontroller. So basically the timers. So timers, they are internal part of the microcontroller. So that's why those interrupts are generated internally, right? they are generated by the software because you are programming them. You are programming like, okay, every time my timer overflow happens, or every time the value of timer reaches the output compare register value, then raise an interrupt. So these are software interrupts. But at the same time, you can also have external interrupts. So external interrupts are known also as hardware interrupts, right? So why? Because those interrupts are raised by events or by signals which are external to your microcontroller, and there are two. They can be triggered by two different type of pins. One is like your interrupt pins, where are INT pins, and you have two interrupt pins, INT0 and INT1, on the ATmega328P, and they can also be raised by pin change interrupt pins. So, and you have lot of them here. So for example, you have like in total 22 pins. So pin change interrupt 0, and then 1, 2, 3, 4, and 5, and 6, 7, and then from 8, 9, 10, 11, 12, and 13, and 14 here, and 16, 17, 18, 19, 20. There is no pin change interrupt 15. There is no 15 pin. There is up to 14, and then 16, 17, 18, 19, 20, and then you have 21, 22, 23. So all of these pins, you can use them like to handle, to receive interrupts from some external devices, right? So here we will not cover the pin change interrupt, external interrupts. If you are interested, you can read the section 17 of data sheet of ATmega 328P. I think I have uploaded at the right when we were starting the semester. At that time point, I have had uploaded the data sheet of ATmega 328P, so you can go and read the section 17. You can easily also Google it and you will find the data sheet. Okay, so we will focus on only on the INT0 and INT1, right? And then we will see an assembly programming example for handling the interrupt on INT0, right? So let's first have a look at the registers which are related to enabling interrupts on these external pins, right? So the first register is a external interrupt mask register. So as clear from its name, you can use it to mask, hide, or unmask, which mean to enable the interrupt on these two pins. So if you write 0 here, it's mean you are saying that disable the interrupt on INT0. If you are writing 1, it's mean enable the interrupt on INT0 pin, and same goes for INT1 bit of the this EIMSK register. So 0 mean disable and 1 mean enable the interrupt. Again, provided that I is set in SREG. So it is not enough only to write 1 here or 1 in this bit. You also need to make sure that I flag in the status register is also set equal to 1. Otherwise, the interrupt will not be enabled. External interrupt control register. So these two interrupts are the interrupts on the pins INT0 and INT1. The input on these two pins, they trigger interrupt only at low level, falling edge, or rising edge, which mean basically like, let's say if you have this is your INT0, for example, right? And this is your like configured as input pin. You don't need to configure it as input or output pin. You only need to enable the interrupts. And let's say if you have configured INT0 or INT1 as an output pin, but your interrupts are enabled, even then the interrupts will be raised. Now the interrupt will be raised in three conditions. What are those three conditions? So let's say that the value on this signal on this input line was this one, right? So the interrupt will be raised if the input is low, right? And interrupt will be raised if there is a falling edge at this point, and an interrupt will be raised also on the rising edge. So like not, but not all of, not at three different positions at the same time. No, you need to configure. So you are saying that I want to enable the interrupt on the pin INT0. Okay, but when the input should be treated as a signal for interrupt. when it is low, or when there is a falling edge, or when there is a rising edge. So you can configure that, or you can specify that. How? By writing value in the external interrupt control register A. So this register has 4 bits which are like used, and 4 bits these are not used. So the first 2 bits at index 0 and 1, uh, actually, let's start from this one because I have animated in that order. So the bits at position 2 and 3, they are used to define uh, the sensitivity of interrupt for int1. So here is the description. So for bits 3 and 2, so if the value is 0 0, it's mean the low level of int1 generates an interrupt request. This one right here, right? And 0 1, any logical change on int1 generates an interrupt request, which mean that an interrupt will be like, if you have this signal here, so an interrupt, and whenever you have a change, which mean both falling edge and rising edge, for both an interrupt will be raised, right? And move this. Okay. And value of 1 0 mean that the falling edge of int1 will generate an interrupt request, and 1 1 mean that the rising edge of int1 will generate an interrupt request. Okay. And same goes for the bit position 0 and 1, but they apply on the int0, not int1, but the meaning of the bit values is same. 0 0 mean low level, 0 1 mean any transition like high to low and low to high, 1 0 mean falling edge, and 1 1 mean rising edge. Interrupt on generator and interrupt on rising edge. Okay. Any questions? Okay, the third register, which is associated with INT0 and INT1, the external interrupt pins, is the external interrupt flag register. So the job of this flag register is the same as the overflow flag, for example, in timers, right? So whenever there is an interrupt on the whenever an interrupt is raised, for example, let's say on INT0 line, so this flag, this bit will be set equal to 1 by hardware, right? By your microcontroller. And if there is an interrupt raised on the int1, so the bit at index 1 of this register will be set equal to 1, right? And again, these bits, they are set when an edge or low level on int 0 or 1 triggers an interrupt, and they are cleared automatically when ISR is executed, just like overflow flag of the timer or compare flag of the timer is cleared by your microcontroller automatically when it starts executing their ISR. Same is true for the uh, int F0 and int F1 of external interrupt flag register. They can also be cleared manually or by writing the code when you write a value of 1 to these flags. Any questions? So when you are, let's say you are doing the interrupt handling and you are writing the ISR, you don't need to worry about clearing them because the microcontroller will clear them automatically when the interrupt will be raised and it jumps to ISR. Okay. Uh, So now let's have a look at an example. So let's say we want to write a program which toggles the pins C3, port C3, whenever there is a falling edge interrupt on int0, right? So basically what we want is this. Where is int0? Yeah, this one here, right? So let's say we are connecting it with an external uh, input, right? So let's say we are connecting with the push button, right? And whenever we by default it is 1, and whenever we provide the low value, so there will be a transition, and whenever there is a transition happens, what we want is that we want the output on the PC3 to be toggled. So like we are generating, let's say, a scale wave here on the output, and we want that output to toggle like whenever the output, not scale wave, but we want that output be toggled every time when there is a falling edge on the int0, right? So how can we do that? uh, Again, okay, let me discard this. annotation. Okay, so again, first we are simply saying that at reset, jump to the start execution at the label main, right? And then we are putting at the address 0x02 a jump statement, which actually jumps to uh, external interrupt 0 ISR label, right? Which is defined here. Again, you can find this address by looking at the interrupt vector table from the slides of the previous lecture. Okay, the next thing we are doing is simply initializing the stack pointer here. And then we need to configure the ports. So our PC3 is the output, right? So we are setting the bit 3 of the DDRC register to set it as an output port. Then we are setting the DDRD, the second bit of the DDRD as the input, which is basically we INT0, right? So INT0 is also PD2. So when you write 2 to the when you clear this bit at the position 2 of DDRD, so basically you are saying configure this pin as input pin, right? And then for the input pin, we also want to enable or activate the pull-up registers. So for that, we are writing 2 in the, sorry, we are setting the bit at index 2 of the port D register, right? So we are done with configuring the port directions. Then the next thing we need to do is to enable the interrupts. And again, that is a two-level process. So first we are enabling the individual interrupt, which is basically the interrupt. Uh, we want to actually just need to write one uh, in this bit of the register EIMSK. Oh no, wait. Let me follow the same order uh, as that shown in the code. So first, as we said, we want to enable the interrupt on INT0, but we want to enable the interrupt at the falling edge, right? So first we are setting the sensitivity of the interrupt, like is the interrupt raised on the falling edge, rising edge, or both edges are only on the low level, right? So for that, for setting the sensitivity, we need to write the EICRA register and the least two significant of this register for INT0, right? So if the value we need to write is simply we need to put 1 in this bit position and 0 here, right? So we are saying, okay, shift 1 to the left this number of time, which basically mean one time. So we will have the binary of 2, right? So that value is written, the binary of 2 is written in R20, and then we are sending it to EICRA register. Now we have configured or we have set the sensitivity of the uh, we have made the interrupt sensitive to the falling edge, right? But we haven't yet enabled the uh, interrupt itself, right? Again, note one thing that EICRA register is an extended IO register, which means that you cannot use the standard IO specific instructions with it. For example, SBI or CBI, right? So that's why if you want to write it, you first load the value in R20 and then you send R20 to the memory location, which corresponds to EICRA register, right? However, EIMSK register is in standard IO domain. So that's why you can directly access it using in, out, SBI and CBI instructions, right? So to enable the interrupt 0, we just need to write 1 here. So here, that's why we are saying set the bit at index 0 of EIMSK. So this will enable the interrupt at int0, right? And then we are saying, okay, okay, here is some code which we execute after enabling the interrupt, this code here, right? And then other than that, what we are, and then we have an infinite loop, jump here, right? Other than that, we also need to write the ISR, right? And what is the ISR? Let me make a little change here just to Okay, I can fix it then after the lecture. No, let me go back, undo the changes. Okay. It is just, I mean, the code is correct. Visually, it is not like readable. That's why I wanted to fix it. So anyway, so here in the ISR, what we are doing is like, what we are doing is we are simply reading the value of port C in R20 register, loading value of 0x08 in R22, doing the exclusive R, which will actually flip the value of the bit at PC3, right? And then we are saying, okay, write the flip value back to the port C and return from the ISR. Now, when will this ISR will be executed? Let's say that we are executing this part of the code, and at that time point, the interrupt happened, right? So let's say we were executing this sequential code after enabling the interrupts, right? Now, let's say our PC was pointing at this instruction, load immediate R31.4, and at that time point the interrupt raised. So externally, we provided a low input, right? So earlier it was high, and when we push the button, now it is low. So there is a falling edge, which means that interrupt will be raised. Now, when the interrupt will raise, the microcontroller will jump to this address 0x02, and it will find that there is this jump statement, a jump instruction. So it will execute this jump instruction, and the control will reach at this point, right? So at this point, then what happen is simply that the output on the port C pin 3 will be flipped, and then you are saying return. So when you say return, from interrupt, so again your global interrupt will be enabled, and uh, you will go back to the same point where you were interrupted. Remember that when you start executing the ISR, your flag register in your flag bit in the register, where is that? I forgot the name. EIFR. So this, when the interrupt arises, this bit will be set equal to 1, right? When you push the button. However, when the control will jump to this location, this flag will be automatically cleared by the microcontroller. So you don't need to, in your ISR, that's why we don't have any instruction here which clears explicitly the flag bit. Okay. So this is how you can handle the external interrupts, interrupt 0 and interrupt 1. Actually, you can also handle in a similar fashion all those pin change interrupts, like 22 of them. But you just need to look at the associated registers. Uh, they have the registers to enable or disable individually all of those 22 pin change interrupts, and then you also have the flag registers, and you also have the register to specify the sensitivity, whether those interrupts are sensitive to falling edge or rising edge or low level or high level. Okay. So the basic idea is same. Like, you need to first enable the interrupt, then you need to specify the sensitivity, and then you need to write the ISR at the specified address in the interrupt vector table. Any questions? No. Uh, if no questions, then that's all for today. Uh, yeah, I think that we are getting very close to our end of the semester. In terms of syllabus, we have covered almost majority of the topics. The only thing which are left is, which I wanted to cover, one more thing was Arduino motor shield, which we were not able to cover. And another topic which we need to cover is the floating point numbers. So we are at interrupts now. So if time permit, I don't know, maybe it depends on the availability of time, whether we will cover the Arduino motor shield or not. But that is not super important, because the thing is, like, it is something which you can add on top of the Arduino board. It is not related to the microcontroller itself, right? So I will prefer to complete the topic of interrupt and then cover the floating point numbers. Uh, So if there is a question or something you want to talk about, please let me know. If no, then that's all for now, and we can meet again on Thursday. Okay, then have a nice day, everyone.